In this section, I'm going to talk about the networking aspect of the human factors and user experience design, especially focusing on the Internet of Things. So when we design a PC or a smartphone, we tend to assume under normal conditions that the network will have a good connection, a reliable connection. The device will be constantly connected to the network. The system will feel responsive to the user's actions. For example, when you press an icon or a folder, it will do something in a quick and responsive way. If the system cannot fulfill your request, it will give you a reasonable feedback and report the progress, like copying a file, or memory is not sufficient to do some task, or the game is loading. And if you are accessing a particular service using multiple devices, it will keep a sync between the different devices, and it will show you the update across the different devices. Both the designers, developers, and the users know that when we are using mobile application that has a backend with the remote web server or is a web application, there's always some of the things could go wrong, like the network connectivity could slow, the connection lost. So if you're taking a Skype call, you could fail, a message could unsend. So we kind of expect that as both the developers and the users. So when we are developing systems, we address these issues by showing some progress bars, or saving some data locally before you send it to the cloud. So if the connection drop, you can resend, and providing some information about what went wrong, like the connection failed, the email failed. But designing IoT is quite different, because they are not designed to connect continuously. So some of the edge cases when we're developing conventional software, like device offline, data that is not being sent, or the connection lost, become the core principles or the core considerations within the IoT, because in the IoT those kind of things happen all the time. On top of that, users are not familiar with the interaction between the traditional computing devices like mobile and tablets, and then the physical objects and the entire IoT ecosystem. For example, when you switch on a button, users expect it to switch on. But if the button is connected to the internet, and it has to go through the internet in order to send the command to the light, and then if the connection breaks or something happens, users are not used to that. So if the light doesn't come on, then it is difficult for them to understand what is going on, because our brains are not trained to understand why the light is not switching on, because we always expected, without even thinking about it, when you put the switch on, it will light up, unless the light bulb is burned or something like that. So there is a gap between what users are used to do, and then when you have the networking in between what they used to do and then what they are going to experience in IoT, the designers need to find a way to bridge that gap in a smoother way, because it is not obvious when something very mundane and everyday task is not responding as they expected. Networking issues that cause user experience challenging in IoT is the fact that IoT devices are only connected to the network intermittently. So they are not connected all the time. And the latency and the responsiveness could also be varied, and the networks are not 100% reliable. Typically, a user interface should respond to the user command within 1 millisecond, like 0.1 second, and then the user will not notice a delay. But if the delay is longer than 0.2 and 1 second, the users will notice, but they will think that the computer is working on the problem, so they'll expect that it automatically gets solved. And then the delay more than 1 second requires computers to display some kind of feedback on what is going on. So there has to be like an icon or some kind of symbol that inform the user that everything is going okay, just please wait. So these are the basic guidelines developed in pre-IoT era. It has been developed by Nielsen many years ago. Even we have the network computers. But the human perception haven't changed since then. So it is the delay that we detect, whether it is a desktop, mobile, or IoT, is pretty much the same. So these are the basic guidelines when you are designing an IoT solutions and you need to think about. Let me now go through the main networking issues in a little bit more details. So first one is IoT devices often connect only intermittently. So many IoT devices are not connected to the network all the time. The key reason is to conserve the power. We already discussed and will be discussing throughout this course that the network communication is one of the most energy expensive tasks in IoT. So therefore, most of the IoT devices, whether you deploy in a smart home area or is it in a smart city or a remote location, you don't want them to connect to the internet and communicate all the time. So you need to switch off the communication radio as much as you can. Because of this, part of the IoT solution or the system could be out of sync. So some parts are up to date and some parts are not, or they may not know each other until it gets fully synced. So there are a number of situations the entire system is not synced because of this intermittent connections. So if you maintain this out of sync system for a longer time, the user experience will feel like there are a bunch of devices somehow vaguely connected, doing different things instead of providing a single coherent solution or a service. On the other hand, when you are developing an IoT solution, you will probably giving the priority for the reliability over the speed, which means that if you want to send a command from one point to the other point over a network across multiple devices, you want some kind of guaranteed delivery. The problem is that this will slow down the process, and then you have no idea when the data packet will reach the other end. So even though there is a communication between two different nodes within the IoT system, depending on the time and availability of the intermediary nodes and the network communication, you might get two different results about latency and responsiveness. So it could be that you perform a particular task and get a response in a certain amount of time during the daytime, and then when there is a significant bottleneck in the network, maybe in the evening or night, it could increase the latency and the time to response. Internet of Things mostly use the traditional internet for the communication. So even though your device may be a couple of devices may be sitting in two different rooms nearby, the actual communication could happen and go around the world and come back. So this is same as sending an email from internet from your house to your neighbor, but still it will go through the entire world sometimes, depending on the routing that autonomously decided by the routers, depending on the traffic and other factors. It could go around the world before it reaches to the neighbor. The same thing could happen to IoT devices, where two devices connecting to each other over the internet might communicate after sending messages throughout around the world. So this is slightly different if you have a smart home hub which has a different protocol, like a low range protocol. You have a direct communication to the hub, but still if the hub is sending data to the cloud for some kind of event trigger or some kind of processing, then again these concept is applied, and then it will take time to go around and come back. Typically in an email scenario, this kind of delay doesn't matter, but in the physical world, we all are used to get a response very quickly. So if you put your washing machine on or your light switch on, you see the light bulb coming up, illuminate, or the washing machine starts. But if there is a 30-second delay from you putting the switch or switching on the washing machine or a light, and then either to start the washing machine or the illuminate the light, if there are 30-second gap, that would be a pretty poor experience that people get annoyed. In this slide, I have presented a small video where they have developed an internet connected washing machine. So I would like you to stop the video now and go and watch that particular small video about the washing machine. So in this video, you can see that the washing machine is instantly responding to the mobile app and which runs over the internet. However, in the real world, you might not see such quick responses. So even 1 second delay to turn on a light could be noticeable to someone not expecting it. So switching on a washing machine or a light is not something that is a mundane task that should not bring users' attention, because there are a lot of other things that users need to focus on. So we don't really focus on switching on a light or a washing machine. It's something automatically happens. We expect, so we know what we are performing the task, but we expect everything else to happen automatically because we are so used to using these physical devices. But if the devices is not working, there is a natural tendency that we will be giving more attention and focus on like what happened, why it is not working. So such attention is not really good because over time the users get bored, then they will probably have a very bad experience. The problem with the internet is there is no way to guarantee the response time because you are not in the control of where the data packets are routed. Previously, we discussed the issue of delay or the latency. But there are certain chances that the data packets might not reach the endpoint at all. So you send a command, you switch on the button, but the light never turn on. So this is the issue when the network is not 100% reliable. So the internet is not 100% reliable. So the packets could lose, and then you will not receive the command back from the cloud. So internet has been developed to maximize the reliability and provide some feedback on whether or not the message arrived on its destination. So that is the whole point of having an internet. But that doesn't mean it is 100% guaranteed. It is highly reliable as long as you are connected to it. But there are a lot of components that could fail within the smart home or within your own premises where the devices are using. It could be like if you are using 3G connection or the local networking routers and switches that you have, or the smart hubs might lose internet connection even for some time, or maybe some devices lose their battery power. So there are a lot of things could go wrong that will could happen that would avoid the message being transferred to the cloud and receiving the results. So this is why we discuss in the lesson 2 about fog computing, because all these networks are unreliable to some extent. Doesn't matter whether it is fiber optic or 3G or Bluetooth. So this means that the edge devices and the gateways need to have some kind of a buffer and temporary store where they can store the data until it is get connected to the network, so you can push the data once the network is on. On the other end, the other recipient should be able to handle some kind of delay. They may not get the data as expected. So you need to think about, when you're designing, what to do exactly from both ends, the sender and the receiver. If the network breaks down, what are the different options and ways that they can handle the situation, reducing any impact on the end users. Let me go through a use case example in order to explain the impact of latency and the reliability of the user experience. First, the impact of latency and the networking reliability depends on what kind of service you are building. For example, if you are developing a large-scale air pollution monitoring sensors which don't connect to the network all the time, it is okay for them to not to communicate in a periodical intervals, even though it may lose a couple of data points. There is less harm for the overall system or the overall goal. On the other hand, if you are sending a command to switch on a light, and you would expect them to respond quickly, and if such data packet or a command get lost, that will significantly impact the entire user experience. So as you can see on the image, this particular light switch is a virtual switch presented on the phone, where it activates the smart plug which will switch on the lamp. So if the packet or the command lost in the middle, that would decrease the entire user experience. Most of the time, you cannot do much about to increase the network reliability. Only a potential solution could have like two different network technologies would act as a backup, and then if the primary doesn't respond, use the secondary. But due to cost reasons, and then it will increase the size of the product, you have to have multiple radios and a lot of complications in the programming and the development part. We'll most likely see that you have to depend on one type of radio, and then deal with the unreliability in the software layer by keeping the user informed and managing expectations. Especially this is true when it comes to the smart home domain. If there are highly mission critical infrastructure like electricity grid or water systems or any industrial manufacturing systems, you probably could think about adding secondary networks that will kick in if the reliability of the primary network goes down for some reason. But that is not something that you would look at when you're developing IoT products and services within the households. One of the ways to manage the expectation is to keep the user informed. So as you can see in these comparative figures, on the flow A, it visualizes what is happening in terms of whether it is switched on and off, but it does not necessarily provide the information about what is exactly happening. In the second one, it says sending, and then it gives done or error. So it not only tells the status, but it will tell what kind of actions happening behind the scene, so the user is informed about what is happening. In addition to the runtime issues, there are other ways networking can impact the user experience. So the first one is the installation phase. So how easy it is to install a new device. This again changes from smart homes to other devices or other domains. So smart homes, you probably end up with the end users are non-technical users, where in the other domains from agriculture to manufacturing or any industrial systems, there are professionals who are dealing with the installation. In smart home or indoor installations, you typically end up using some kind of pairing mechanism. For example, if you're using the Bluetooth, it will require to pair the two connections, two devices together. When it comes to pairing as well as connecting to the home networks, so you need to provide easy to use interfaces and help them to find which Bluetooth devices, because if you presented some MAC address or a particular number nobody understands, they will be struggling to connect to which network or which kind of device. So you need to have a meaningful terminology when someone is scanning the area, so they can pick what is their device is, or find a mechanism to actually see what device is what from the Bluetooth point of view. Then throughout the pairing process, you need to show some kind of visualization on what is happening when there is a request is made, whether the other device has received that, some kind of acknowledgement. So you need to think about both ends of the two devices, and if both ends doesn't have the user interface, maybe one device might have a few lights or some kind of actuators or any kind of vibration mechanism to represent what is going on. The other end might have a proper a mobile kind of screen. So you need to think about how you're going to use different kind of sensors and actuators and screens and visualization mechanisms to inform and update the user and give feedbacks on real time on what is exactly happening, what is intended to happen, and what will happen, and some kind of progress, overall progress of the installation process. And then they need to be confident that once you set up that they are connected. So you need to do some kind of demonstration about what the devices can work together, or at least force them to do some kind of interaction so they get comfortable with the fact that they are connected. Another important issue that related to networking of smart devices is the interoperability. The question that we need to ask is, does the devices work with the other devices that already exist in the network, given that they may be developed by different manufacturers and also they use different communication protocols. For example, if you look at the devices in a smart home domain, you probably see three main different protocols in addition to the proprietary ones. So typically manufacturers use Bluetooth, Zigbee, and Z-Wave. So you need to think about how these devices will be work together and interoperate successfully when you're designing your application. Because if they are not communicating properly, that would impact the entire user experience. To address the interoperability issues, either you will need to use some kind of a converter, probably within the smart home hub, that will support multiple communication protocols, or try to adhere to the three common protocols widely supported: Zigbee, Z-Wave, and Bluetooth. From the device's point of view, it would be quite challenging to add multiple radios due to the energy consumption and the cost of the devices. But the home hub is the best place to embed the capabilities of multiple protocols and protocol conversions. Another networking issue that you need to address is the addressability on the internet. The question is the device you want to directly addressable on the internet, or does it need to be connected via gateway? So sometimes it is not necessarily to be able to connect it to the device remotely over the internet directly using an IP address. For example, if it is a security camera, there may be a use of directly connecting to the camera. But if it is a other device, you might connect it through the smart home hub. However, if your particular device you design is internet addressable, that will help to interpret better, because the other devices developed by other manufacturers probably can connect it to your device directly and communicate with independently from a gateway. This is also helpful for machine-to-machine communication. It may be less useful within the smart home domain, but if it is manufacturing or industries, there are where a lot of machine-to-machine communication happen. So individual addressability would be an advantage, where they can communicate with each other without an intermediary device or gateway. In this figure, you can see there are different devices are being connected to a single phone, a single gateway. It shows different objects that are being developed by different manufacturers can communicate each other because it belongs to a single ecosystem. Having these interoperable connections allows third parties or the end users to develop complex interactions or scenarios where certain events and devices can be combined into a sequence of actions. For example, you may have already seen that some of the sequencing mechanisms like if, then, and that, where if a certain condition is met, then the sequence of events related to different devices could happen. For example, if it is a morning routine where you wake up, then you can program the devices to perform sequence of actions, having the morning wake as a initiation point, and then switching on the lights or the coffee machines or the other appliances. So you can have these complex routines if they are, even though they may be developed by different manufacturers, if they are interoperable, then you can build these complex routines. We have already talked about the architecture from Internet of Things system perspective. In this slide, over the next few slides, I would like to talk about the architecture from the human factors point of view. When we are connecting together different IoT devices, there are 5 ways to do that. You can have a dedicated gateway. You can have the smartphone as a gateway. You can directly connect the device to the internet. And you can have device-to-device connections as well as service-to-service connection. The first option we have is the dedicated gateway. A dedicated gateway is a combination of hardware and software we can deploy in any environment. Basically, their job is to translate from internet protocol to the other local non-IP protocols. So the gateway will do the translation between different protocols as well, from Zigbee to Wi-Fi, Bluetooth, or any kind of conversion. It could also act as providing supporting storage and other kind of data processing activities as well. So the gateway could be accessible over the internet. It has an IP address, but then it will receive the commands from one particular device and then look up for the address that the command need to reach, and then will do the translation from whatever the protocols that is required to reach that destination, and then it will do the translation for you. This allows easily connect different devices in a home network, but the problem is that the entire network depends on the gateway. So if the gateway fails, there is no way that the devices could be connected together or talk to each other. Most of the leading smart home solutions has their own gateways. So you can see a couple of them here in the images. But in the industrial version as well, you can see industrial gateways, especially created in a more rugged form to tolerate high temperature and vibrations, but the functionality is pretty much the same. As we discussed before, gateways sometimes play the role of the fog node as well, which will do the local processing, but it is not always go hand in hand. There are two different functions, but sometimes they come together to perform as a combined version. Most of the gateways, especially the smart home ones, are using Wi-Fi to connect to the internet, but sometimes they also have a SIM card that will have a cellular data backup that can use if the primary the Wi-Fi network disconnects. And also in the industrial setting, you will also see gateways in protocols related to LoRaWAN, which is a long-range protocol, which also most of the time depending on a gateway, which will do the time synchronization between multiple different devices. In that case, the gateway determines when it allows the other LoRa nodes to be connected to that gateway in order to do the communication. So in this figure, you can see the gateway connected to multiple edge devices, and then it is connected to the broadband router and access to the internet. And then the UI or the mobile phone can connect it to it, as well as the other third-party services and the applications. Gateway translate between short-range protocols to internet protocols. It also provides a security firewall. It could have different functionalities from intruder detection, such as malicious attacks on the home network or any local network, because all the traffic has to go through the gateway, which allows it the opportunity to look at each packet and see are there any anomalies. So it becomes the brain of the system as well as the secure protection. So that is the strength of the system in terms of the security, but also it creates a one point of failure, because if the gateway fails, then the entire network stops working. The second common pattern you can see is the use of a smartphone as the gateway. Most of the wearable devices and healthcare related devices use mobile phone as a way to reach to the internet. So wearable devices will have a limited battery consumption, which leads to the choice of short range, low energy protocols, which means it cannot directly connect to the internet. So it has to use some kind of a gateway to connect to the internet, and because it is personal and individual, and we have the assumption, and we also saw the numbers before, most of the people owns a smart home device or a mobile device. So it will use the mobile device as a translation gateway to reach to the internet. So you can see that data flow in this particular figure. So you will, the wearable device will communicate with the phone mostly using Bluetooth. That is the short range protocol that most of the mobile phone supports. And in a rare cases, it could also be NFC and RFID as well, but they are not designed for communication per se. they are more focusing on tracking items, but it still use the mobile device as the gateway. However, if you're planning to use a mobile device, you need to think about that you are not consuming unfair amount of energy of the mobile device of the user, because if your particular application start using a lot of energy out of the mobile phone, it will drain the battery, which create problems for the end user because they need to keep charging it. Or you need to think about whether is it worth forcing the end user to buy a particular tablet device dedicated for your particular IoT application. It might work, it may be justified depending on the application. For example, if it is a serious healthcare application that help significantly to a particular individual, or if it is helping like carers or any other more serious end of the healthcare applications, or any scenario you can justify to have a dedicated mobile device to support the IoT application, then you could incorporate that into IoT application design. But in a normal everyday applications, it will unlikely that someone would dedicatedly buy a tablet device or a mobile phone just to support the particular application. So you are basically renting out the space, time, energy of the mobile phone. So you need to make sure that you are not overusing the resources. Another option you have is a direct internet connection. Some of the devices you could design in a way that it will directly connect to the Wi-Fi, or use cellular to directly connect to the internet. Power consumption is a major concern in this pattern, but as you can see on the image, if you are developing a smart plug, which you pretty much don't have the constraint of the energy, you can directly connect to the internet because you are already connected to a power source which is permanent. In this case, you can directly connect it to the smart plug from outside and switch on, switch off. There are a lot of things you can do directly without any gateway. It also help and make sense, especially for smart plugs, because if you're outside of the home and then you want to switch on and off, you don't want to create a dependency having a gateway, because then if the gateway for some reason broke down, there's no way for you to directly communicate with the smart plug, which may be connected to an iron or anything that might have a hazard. But if it is directly connected, it could be one plug is broken, like one plug connected to the iron, but the other one connected to maybe some other appliance like a multi-cooker. Then you can still communicate and control them remotely, even though the one might not work. So it reduces the dependencies and add more resilience, but the downside is it mostly work if you have a good power connection to the particular IoT device. So in the figure, you can see that now we don't have any kind of gateway directly connected to the internet, and the rest of the data flow still stays the same. Another option you have is the device-to-device communication. This is somewhat more common in the industrial setting than the smart home setting. The idea is that the edge devices would connect to each other and communicate with each other without a gateway. The problem is that if the devices are manufactured by different people or different manufacturers, the both communication layer as well as the application layer protocols might not be compatible, which will stop the communicating between different devices, because the gateway helps to translate these communications typically. And then you can see that if there are two manufacturers, then there are two different ways of communication. And if you add about 8 different manufacturers, it could be end up with 8 different communication protocols, and then each device has to have a large number of adapters to support the communication and translation. So this could be a little bit more bulky, but in the industrial setting, it is easier for companies to come together and come to a standard, so they can each of the devices can be communicated. So you can see on the image that it stays as the same as before. So you have a gateway, but then it also allows a secondary communication between two edge devices. So it's slightly more dangerous to assume that you can completely depend on machine to machine or the device to device communication. At the moment, it is more like a supplementary communication where you have the gateway, but you also have the edge communication between the two devices. If they are permitted, for example, if you are manufactured by the same company, then you could assume that they could work together. So this helps to add more resilience to the entire IoT system, because now if the gateway broke down, at least some of the devices can talk to each other. You could see a limited number of examples in this area where your security system is using the smart speakers to communicate. So I have presented a video about the machine-to-machine communication. Please stop watch this video and go and watch that one to understand the machine-to-machine communication better. There are a number of key challenges in machine-to-machine communication. First one is about the discovery. So how do you discover nearby friendly devices? And then how do you know the identity of the services running on these devices? Because how do you know they are not compromised or they are not evil devices that are trying to connect to your network? And how do you adapt to devices that are coming and going? Because the IoT devices are mobile, and then they should be able to connect to a device for a short period of time and then leave the network as a natural course. And then how do you manage the device? And then the diverse behaviors as well as the communication protocols. Each of them might have different power sources, and the communication protocols, each one has their own priorities of saving energy. And then communication patterns. So how do you manage those heterogeneous devices? Which also leads to the interoperability, especially if they are running an operating system. So how do you make it work and synchronize? And then how do you exchange information? What is the language or a common standard that could be used to communicate? Because it could be very similar to like one person speaking English, the other person speaking French. Especially the devices are also like that. If they talk different languages, how do you? So what will be the language as well as the format or the structure? Because the communication has to be some kind of a structured communication, which when somebody sends information over the other device should be able to interpret. So it has to be some kind of a standardized information. And then how do you make it secure against the nearby actors? What we see today in the IoT marketplace is more like independent manufacturer-based silos. So you can see the laundry has their own cloud. Security systems might use their own cloud. So depending on the manufacturer, they are constrained into the limited ecosystem, and their communication between other devices are very limited. Maybe like switching an on and off kind of capabilities may be possible between the different manufacturers if you have a hub that could actually translate. but other than that, it pretty much directly sends the data to their own cloud, and then it's manufacturer based constraints or the siloed environment. This figure shows what we say machine-to-machine communication. So you can see there are multiple different devices, from security cameras to computer screen, coffee machines, smart speakers, smart lighting. They are working together, and then they are using each other's interfaces, inputs and outputs to communicate with the end user. So you can see someone at the door, and then the lights will illuminate to visualize that to the end user, consumer. And then the coffee is done, it will notify through the smart speaker. So in this communication, which we call direct communication, which is faster, efficient and secure as well, because it is device to device communication. So you can have encrypted communications. You don't have to trust a third party to intermediate the communication, because we have a centralized control. It adds additional vulnerabilities, because if someone deploy on some kind of malicious applications within the gateway, all the devices and the data goes through, that could be compromised. In this way, there's no need to go out to the cloud and talk to the devices. So it also increases the resilience in terms of broken the internet communication from the house, but the local devices then can talk to each other. As I told you before, each of the devices have their own capabilities. Ideally, these capabilities could be discoverable as services, as interfaces. So some of the devices might have the lights, some of the devices might have different types and the levels and complexities of user interfaces, displays. Some might have the capability to make sounds. The others might have the capability of make vibrations or any other kind of actuation. So when you have this bunch of devices connected to each other, it allows you to use others' capabilities. If the particular IoT device that your particular IoT device don't have a particular capability, instead of trying to have something which make not sense, because sometimes if you want to keep a low-cost device that very small, you might not be able to put a display into it, even a small one. But if you have the other devices, and if there is a machine-to-machine communication established, then you can use other device like a TV or even the screen of the microwave as a way to display, to communicate whatever the message you want. This is the whole advantage of having device-to-device communication and shared capability. The final architectural pattern that we need to discuss is the service-to-service connection. This is a way that you can connect different devices developed by different manufacturers through a service integration rather than having a shared gateway. Basically, you are using APIs and then making it available for other manufacturers in a collaborative way, so they can use that to initiate different communications. For example, if you have an activity monitor which can detect whether someone is waking, and then it could trigger the thermostat developed by a different manufacturer by communicating directly to the API. So now the API sits in the cloud, but there is no gateway. So as you can see in the image, you have built a communication between two IoT devices without a gateway intervening. So of course, one of the devices have a gateway, but that gateway is used to connect to the internet, but not to connect to the device. So the message loop goes through the internet API and then to the other device, not the gateway. So the other way is that you have the gateway and directly connect to the gateway. So in that case, you don't need to go over the loop of the API, just you have the two devices directly connect to the gateway. But the difference here is that it goes through the internet, goes through an API. So the gateway here in this figure is used because it cannot communicate. The particular device is not capable of connecting to the internet directly. But it does not involve in the communication between the two devices. It's just a way of connecting to the internet of one particular device. The other device is capable of directly connecting to the internet, so it does not require a gateway on that end. But the key here is that the communication, connection happens through within the cloud, completely cloud dependent now. If the cloud connection drops, the entire system breaks. But now it's working through the open APIs. So you can hypothetically think about this is more like a cloud gateway, but it is API. So each communication goes through different APIs. So it's not a single cloud gateway. But you can visualize in your head this is as a virtual cloud gateway / API kind of scenario that you can use to establish communication between two devices. The overall user experience could also be affected by the system's architecture, which will determine the flexibility, responsiveness, and reliability of your system. For example, if a sensor is directly connected to an actuator, then the behavior would be quite quick and robust. But it is inflexible because it is difficult to change and adapt over time. So less scope for adding changes or system functionalities. If the path of the sensor goes through to the actuator through a gateway, then there are more number of pathways that the communication could break. And then you need to handle more bugs related to the communication, or you need to have more application code to handle the latency. But in this case, you have more flexibility. So this is a trade-off between having more flexibility, but it could also have more disconnections and more complications when to debugging. Because now you need to think about what went wrong from either gateway to the device or the gateway to the actuator or within the gateway. So you have three nodes, the sensor, actuator, and the gateway, and then two different communications. So all five of things could go wrong. The flexibility means that then the gateway can control multiple devices. So when your device is connected to the gateway, it has the ability to communicate with all the other devices on the gateway. If the path goes through the internet, that has more greater potential in terms of you can add more functionality, you can easily update, nobody even knows, because if it is a home hub and if you want to add some AI functionality or add more services, you technically need the support of the end user to do that, because they need to either download kind of a service app or update firmware or something. But if it is completely internet driven, then the manufacturer or the software developer can actually update the internet services. The user don't even need to involve at all. We saw that if you are working through the API based communication, which is completely internet only, then there's quite a flexibility on that end. You can update anything at any time. A user even don't know. So there will be no new functionalities will be popping up, but the user don't have to do anything. But the downside is now you have the internet, which means unreliable and more latency. But more good side is that you have the ability to upgrade anytime. You can also combine different architectural pattern we discussed earlier. So you can have the cloud API version, while you also have a gateway on the edge or the home, which adds you more flexibility. But that means you need to sync all the components, because you cannot have different state within the home and cloud and run a system for a long time. It could have out of sync time per frames because of the internet connection and the loss of the networking. But it has to be, majority of the time, it has to work on sync, which means now you need to do a lot of programming, a lot of coding on different nodes to make sure that everything is synced, which will add to the increase in cost, but also it will add more flexibility. For example, if you have a actual hardware gateway, and if you have a virtual gateway, you can provide certain functionalities that the hardware gateway does not have, and then the cloud can actually perform that certain task, let's say an AI task, which will detect certain sequence of activities or some security video analytics, and then you can actually convince the either you can keep it running on the cloud if that there's a necessity to do that, but also you can ask the end user, the consumers, to upgrade, saying, hey, we were providing this functionality for you over the cloud, and then it seems like you are happy with that, so why don't you update it? Because that is a more convincing case to go through a little bit more management task of the system in order to get more benefits. So you can say the latency will be reduced and things like that. And there could be some functionalities that is quite impossible, or for some commercial reasons that they don't want to implement in the gateway, because the gateway is not doesn't have sufficient resources to do that. In that case, you can run it separately in the cloud and the gateway. So the gateway will provide the basic functionality, and the cloud will provide more advanced functionalities which they don't want to share or deploy locally. At the same time, you can have machine-to-machine communication, which means another type of flexibility. Now, the previous case, if the internet breaks, the gateway can perform, and then even the gateway breaks, then the machine-to-machine would work. So there are 3 different layers of resilience. So the more you combine, the more it's complicated, but it will have more flexibility. So it's a trade-off between what kind of flexibility and then commercially viable, which means how much it costs to actually implement all these different scenarios. And also depending on the practicality of the devices, the size, the energy it has, and the communication capabilities they have. So all these different architectural patterns can be combined in many different ways that you think. It will bring different pros and cons, but it is up to you when you're designing IoT system for a home or an industrial domain or application. You need to consider all these options and come up with why you pick the particular one or a particular combination. So then you can justify that is both commercially as well as to the consumers from the convenient and the long-term usage point of view. We already implicitly discussed the advantages and the disadvantages of a gateway. But here I have summarized them in a one slide. So the disadvantage is that gateways are time consuming and costly to develop, especially due to the lack of standards. And also it creates one potential failure, because if the gateway fails, either due to technical reasons or the user forgot to plug the gateway or accidentally unplug, the system will stop working. But there are a lot of advantages as well. So when you have a gateway, you can have the network communication management and security to be passed on to the gateway rather than ask each individual device to do their own. Gateways make it much more easier to install and maintain multiple devices, so you don't have to go and configure each device individually. It is also low latency. The commands can be usually passed on quickly over the network, to the internet. It can, up to a certain level, can perform its job without even the internet connection drops. So it can communicate with the local devices without the internet. And finally, it enables devices to support different network protocols and interoperate, because it can act as a translation device between different protocols from Bluetooth to Zigbee to Z-Wave, and also use cellular and Wi-Fi to communicate with the internet. This is true for both the industrial setting as well as the smart home applications. Over the next few slides, I would like to talk about a little bit more on the networking and communication technologies and protocols. I want to stress that we already discussed the network communication in a separate lesson. So my objective is not to repeat the same content, but briefly talk about these protocols from human factors point of view, why it matters in the design perspective. Previously we discussed about the more technical side of the network communication, the internals and how they work. But here I'm talking about what are the how they would impact the different network communications in terms of the human interaction and human factors. When you are designing an IoT system, there are three primary ways to connect to the internet. So you can use the Ethernet cable, you can use Wi-Fi, you can use cellular. So Ethernet is wired technology. So if you are having a device that is unlikely to move around your house or a particular location, then it would be more suitable to use Ethernet, because you can have a strong, consistent connection and the bandwidth for that particular device. So Wi-Fi is the most common way of connecting IoT device to the internet or to the hub within the home. The problem that you need to look for is that if something misconfigured, it is quite easy to reconfigure if it is a tablet or a mobile or a laptop. But if you are configuring Wi-Fi for a washing machine, it could be a little bit more complicated to reconfigure and fix it, especially if you're asking to do this task by a non-technical person. Cellular is a choice that you can use for quite mission critical. There has to be an importance behind the requirement if you're asking someone to use 3G or 4G. For example, in this use case, they talk about a pill bottle, which has a sensor and a small gateway, which has the on cellular technology to communicate with the internet. The healthcare products like pill bottles might be important to have direct communication, mostly because they might make the argument that because it is critical and somebody need to see that whether the person took the pill or not remotely, maybe a family member, maybe a carer. So in that case, if they are connected to the gateway, it might add additional issues, like if the gateway breaks down, then what happens? Or it could be like if it's a remote area, you don't have the good internet connection through Wi-Fi, or the house doesn't have the Wi-Fi at all because the person doesn't use the internet per se. If it's an old person, maybe living alone, so in that case, maybe this is the best option. You have the gateway directly communicating, so no requirement for Wi-Fi or configuration or anything. If it is a SIM card, you put the SIM card and it works. So it is not about there's a one way fits all. It depends on the application and the stakeholders and who are going to use and how long, and the energy and everything need to be considered when you are picking these choices from the human factors point of view. Because some of the technologically, we might say, okay, this particular protocol makes sense, but when the humans are involving, for example, if it is like rural areas that might not have the internet connection and the house occupant has no idea how to connect it or maintain it, then if you are a carer or someone who go and put that Wi-Fi, it is unlikely that the person will be able to maintain it unless because if something went wrong, then you have to go and fix it, or you don't know what is going on. But for a SIM card, this very likelihood that it could work. The only worst case is someone unplug this particular device from the power, the small gateway that communicate with the 3G. So there is still risk, but it is much more convenient for everyone to use cellular than Wi-Fi. But there is also a cost attached to the particular communication technology. And also, if this is a purpose is to enable these pill bottles or some kind of healthcare matter, if you put a Wi-Fi, then the household people might also use Wi-Fi for watch YouTube or anything else. But if these particular devices are funded and provided by some kind of a organization focusing on health matter rather than providing Wi-Fi to the house, then it is become also a conflict of kind of interest, because now you need to block any communication. If you try to deploy a Wi-Fi device or a Wi-Fi network, you need to make sure you are so this network is only be used for the particular health issue or healthcare management related, not to watch YouTube or Netflix. So then it becomes more challenging to block and maintain these devices. So if you have a 3G SIM that integrated into a device and just plug it, it's very difficult to misuse it. So human factors actually brings a lot of constraints and opportunities to think about the design. There are a number of protocols widely used in the local networking which are not IP based, so which means that they have to use a gateway to directly communicate with the internet. So increasingly we see that edge devices or the IoT devices are being embedded with communication protocols that can directly communicate with the internet. But at the moment what we are seeing is more like a transition period where majority of the devices use low power local network protocols, and then the gateway do the translation. So what we widely see is Bluetooth and Bluetooth low energy. We also see proprietary radios developed by different manufacturers, and then Zigbee and Z-Wave, RFID and NFC, and then the power line networking. Bluetooth is the one of the most common and widely used local network protocols. There are two flavors, classic Bluetooth and Bluetooth low energy. Classic Bluetooth requires a paired connection to maintain in order to communicate, which means that Bluetooth radios are constantly in use, could drain the battery quickly. So the Bluetooth low energy ones are connect and transmit the data at regular intervals, or when they have something to share, which means that is good for in terms of preserving the battery life. They are typically used in conjunction with a mobile phone, but you could use without a mobile phone which may have a gateway that has the Bluetooth communication capability. For example, we have seen like smart speakers and smart home hubs are using Bluetooth to communicate with each other. You can develop proprietary radios to do the communication. We have seen the baby monitors are using this kind of proprietary networks. One of the key reasons could be to be reliable and cheap, because there's no license fee for manufacturers to acquire if they're using their own radio. And then some of the protocols might be determined as unreliable for some applications. But interoperability becomes a significant issue, especially if you are trying to develop an ecosystem. Then it is quite challenging for other people to adapt your particular communication radio for other people's manufacturing process. Even you may be happy to give it free. So that is something you need to think about when you, if you determine to develop your own proprietary radio, whether that the reliability is an issue, whether do you think that are you building an ecosystem around it, or do you want it to be interoperable, or do you have any plans to develop another add-on or adapter for the other people's gateway so they can connect your device to them if that is necessary. So it is an option that you can explore depending on the application domain you are working at. There is sometimes of argument that it might bring a little bit more security rather than using protocols, but it mostly like an illusion of the security, because it is proprietary radio, that doesn't mean that it is secure. But the malicious parties might be less familiar, but it is a matter of time they will get familiar. So if someone is arguing for security, it is pretty much the illusion, not the actual security. The next choice we have is Zigbee or Z-Wave. So both are low-powered radio networks suitable for battery-powered devices. So if you are designing for home automation or smart manufacturing, indoor environments, you probably end up using either of these protocols. It has a similar range to Wi-Fi, but also it allows to develop mesh networks, which Wi-Fi does not provide. It also has the capability to add repeaters directly powered by energy sources, direct power sources. So then you can extend the range of the network. Neither of them supports IP networking, so you cannot use for internet communication. There could be minor issues in terms of the risk of interference, because all the three Wi-Fi, Bluetooth, Zigbee all operates on 2.4 GHz frequency. So that is something you need to think about. For example, if you are max out your Wi-Fi network transferring videos, your Zigbee light switch might not work. This is a very rare case, but you need to think about this using these frequencies in the similar spectrum. This interference could be very, very rare, but it's worth keep in mind when you're designing and testing these solutions. These are one of the factors that could come into play. RFIDs and NFCs are the other options. They are both very short-range protocols, especially used for tracking. If you have any particular tracking requirements in your application, you could probably think about using one of these. So RFID is the radio frequency identification. It comes with both passive and active RFID tags. They could have about 10 to 100 centimeters. So the passive one is powerless. So it's basically the signal, the reader send the signal, and then the tag get power from the signal and then respond to it. So you can read whatever inside the tag. And then the active one, which also has their own power. So it could have a more longer range than the other tags. So you can use this kind of tagging for tracking your pet. So the pet, whether they are going out of the house or not, you can see on the image on the top, that is one of the devices that a cat can go out. and then also the pet feeder, which when the pet comes and eats, then you can find out whether the pet eaten or not if you are outside of the house. So it keeps track of what they are eating and when they are eating, because if you put a tag on their neck and then the reader on the device, you can track how many times they reach and how much they eat and what time and so on. NFC, so near field communication, also using for tracking, pretty similar to RFID, but NFC is widely supported within the mobile application, so you can use for mobile payment, so the mobiles can read the NFC, so that is the advantage of RFID, but it has quite a small, very short range, few centimeters compared to the RFID. So you have to intentionally sort of put it somewhere in order to track it. It could be useful than RFID sometimes for like payment. So you don't need to go nearby the payment. You have to actually put the mobile phone or your smartwatch or whatever the NFC tag you have onto the payment. That's only it will work, which is also good for if you are managing a stadium or any museum where you might want to put a handband on the guest so they can tap in, so you can track those kind of things. It is could also use for transportation, so you can someone tag the to open the gate to get into a transportation network, physical transportation like trains and buses. NFC can also help to simplify the configuration process of the other devices such as Bluetooth and Wi-Fi, because NFC can communicate with any mobile phone. So you have put an NFC tag on the device and it will tell the mobile what to do, how to do about the particular IoT device, which may be not familiar to the end user. So it's more like NFC could act as a guide to the mobile phone, and then mobile phone can guide the end user. More recently, NFC has also been used to data communication through Android Beam and Samsung S Beam are the example implementations where they use NFC to communicate between two devices, nearby devices. So you need to almost tap the device to each other in order to make this work. But this could be another way of either helping the configuration process or setting up. So you can tap your new device with the old device, and then it will transfer the communication and other configuration parameters to the new device to simplify the process. So these are some of the options that you can consider when you're designing your IoT system. Pipeline networking is another option which you can use within your IoT application design. When the Ethernet is not available and then the wireless communication is not too reliable, you could use the electrical power cables to do the network communication using a standard called power home plug. So basically you need to plug an adapter to the power socket, as you can see on the image, and then it gives you both power and you can clip a Ethernet cable, and then you can use that connector to the whatever the device you want and do the communication there. It is quite simple to set up, and then the power line network is quite fast, secure and reliable, but also it runs through the concrete floors, which might cause problems for Wi-Fi. However, you need to keep in mind that it acts as a radio transmitter. So in some countries, this could be classified as a form of broadcasting, which you require a license. At the same time, another downside is if there are multiple devices are plugged in, it is possible that the signals could be interfere from one another. This is not a popular approach of networking, but this is one of the possibilities. If none of the others are working for you, you could consider this as an option. Here I would like to briefly summarize some of the things that you need to think about when you're designing IoT applications and thinking about the communication between the internet and the edge devices. At the moment, there is no standard way to translate TCP/IP to non-IP local protocol devices such as Bluetooth or Zigbee. So this means you have to depend on custom translations which are built into individual gateways, which means that two devices, for example, heating system and security system, cannot talk to each other directly. They has to go through a gateway, and within the gateway there has to be an app. So the functionalities depends on how the gateway app is implemented. However, there is a trend and growing movement to bring the IP-based communication to the edge as well. We have seen that there are some protocols, low power IP protocols being introduced that allows to communicate, allows for two devices to communicate each other directly. However, these technologies are still in the early stages. However, in order to develop a true Internet of Things, we will need to have the capability to talk to each individual device separately, so they can talk to each other without any intermediary gateways or conversions. Once we acquire the capability for having one IP address for each device, we can communicate in a much more flexible manner, because now the functionalities are not limited to the one that implemented in the gateway application. Two devices could talk to each other in a more free manner. So you can imagine this is more like having two people conversation or having mobile phones, which they can talk to each other at any time. But the current IoT, which is the gateway dependent approach, you can think of like the old school telephone network, where you want to take a phone call and then you need to talk to the switch box and then say, hey, I want to talk to this person, and then the switchboard will dial the number and make the connection. Probably this is how we took phone calls many years ago or decades ago. Maybe you haven't heard about that, but so this is how they communicate through a switchboard. And then once you have the identity, you can create profiles, you can track the behaviors. For example, if it is an electric car, if you go to a different friend's house and do the charging, then the charging bill could come to your house because they know that it is your vehicle. Similarly, you know that if you have a washing machine, if there are individual parts that are worn out to be replaced, then you can the manufacturer can actually send the parts proactively, and if there are certain parts need to be changed over and over again, so if you see certain patterns, then you can track whether the consumer or the end user doing something wrong, or if the different part of the machinery is wrong, and then that impact the worn out of the other parts, or whether the electric connection is not properly configured, maybe that is affecting. So if you have the identities of individual devices, you can actually track the history and then make a lot of decisions based on that. As we already know that IPv6 is coming up. So the previous version, IPv4, didn't have the enough number of addresses. It's about have 4 billion possible addresses, which is not enough to be given to each individual device. That is one of the reasons that we don't have IP connectivity, other than the technical issues like the energy consumption of IP-based protocols. However, the IPv6, the new version, can provide 10 IP addresses for every atom in the world. So pretty much you can provide one IP address for each device. When we can allocate IP addresses for each device, it allows us to run high-level protocols on top of that. So we could use the same application protocols that you talk to home devices on them as well. However, the downside is when you are opening up the devices to the internet directly, now you need to think about security as well, because previously it was behind a gateway, which is difficult for someone from connecting from internet to get into a particular device, because gateway limits what they can do, what depending on the application. But when you are open to the internet, it also previously we discussed that increases the flexibility, but the flexibility also comes with the security risk, because now you are opening up the attack surface and you probably don't know what the attacks could be, because it's pretty much more like a computing device now. Having said that, all the low power network could still be forced to run on a gateway based mechanism, because the IP tend to consume a lot of energy. Therefore, you still might need to use the gateways for low power networking. But now you no longer need to connect all the devices to the gateway. You can pick only the devices that are unable to connect directly, very low power, small devices, and then the gateway could be quite simpler, because now the washing machine or the microwave or the oven or the bigger ones, you don't need to connect through the gateway, which at the moment everything has to go through a gateway most of the time. At the same time, the role of the gateway will still remain for a while, or most probably indefinitely, because gateway also plays the role of the fog computing, which means that the ability to run and communicate a local area network without the internet. So if there are any AI or intelligence embedded in the collaborative nature of these devices, these intelligence might not be stored in individual devices. Individual devices might be able to communicate, but there has to be a way or a place for this intelligence to need to be processed. So if you can gather the data, machine-to-machine communication might collect the data from different devices, from microwave to washing machine or a TV, or even in the manufacturing settings, this could be like an arm or a robotic arm or a belt. So once you have the data, somebody will need to process. Because communication is more like the automation part, but to generate the intelligence, you need to collect the data and analyze. So either the individual devices has to take responsibility of doing the data processing. For example, on behalf of the factory, robotic arm might do the processing, but it's more likely that there has to be an edge device which has more computational capability and resources available, where they will bring all the data together and do the processing locally. So even though the gateway functionality in terms of the communication or the network protocol translation may go away with the adaptation of IP addresses and direct connectivity, but from the fog nature of the intelligence and data analytics sense of point of view, you will still will be required to have some gateway to remain on place. Broadly, there are three network communication patterns. So the communication we are talking about here is that how devices are sending and receiving data over the network, which are primarily governed by the protocols in the application layer. Understanding how the data flows around your IoT system architecture will allow you to understand how responsive the entire system would be and how rapidly the data will be synchronized across different devices. So the three different patterns we are talking about are the push, pull, and polling. In high level, push means that the sender, the device, would send something and then push the data to the other end. Or the cloud is doing something and push the command to the end device. So one device is pushing data to the other end. The pull means you are requesting. So you are connecting to the cloud and accessing data, or you are connected to the device and pulling back the data to the cloud. So you are initiating the communication, and then you are requesting the data or command. The polling involves more like an intermediary, where you can think about like you have a device and you have the other, maybe another device, but they're not communicating directly. They communicate between intermediary. So you on the one side, the sender will somehow send the device to the intermediary. So the intermediary will keep the data, and then the other device does not know when the request will come. So it will periodically requesting and sort of looking for data. Do I have anything? Do I have anything? So that is what we call polling broadly. Each of these have their own pros and cons, and suitable for different situations, as we discuss over the next few slides. As a user experience designer, there are a number of things you need to think about when you are planning or designing the network communication patterns. So the first one is how the devices transmit messages from the network. Does it push them at regular intervals, or when there's a condition met, like an event base? Or only does it transmit when a client device or a service request, or when someone asks, like pulling method? The next question is how does the device receive messages from the network? Do they get pushed data from a service or another device, or does the device need to request them as needed? How frequently the devices are connected? Is it constantly connected, or connected at regular times, or only connected when it is need to be for some event, or some kind of a sensor reading or actuation happens? Then there are a few questions around how fast the instructions or the data may get through, or data may need to get through. How long does it take the devices to establish a connection? How fast the connection would be? How much data to be sent? How directly it may be routed? Because whether it's local, whether it is sent into a local gateway, fog node, or is it directly the internet? Does it need to be come back, or to a different manufacturer or a service? So there are a lot of questions like these you need to think about and plan ahead, and mix and match the architectural patterns and other design options that we discussed earlier in terms of protocols and technologies. We can discuss these network communication patterns using this example. This is an example of where a mobile application is used to change the temperature through a gateway. So the scenario is that a battery-powered heating controller using Zigbee contacts its gateway every 2 minutes to register its status and look for new instructions. We call this check-in process as polling. The controller does not know when the new instructions would come, so it has to regularly keep checking. So on the other end, the user turns the heating up from 19 to 21 on his mobile app. And then the app passes the instructions to the internet service. And then the gateway device usually do the polling from the internet service to see whether there is new instructions at regular intervals. So in the image, you can see that the mobile app is polling every 30 seconds, and then the temperature device is polling every 2 minutes. So the gateway has main power, so it can poll more quickly, perhaps every few seconds, if that is necessary. If the user is in front of the heating controller, they will notice that it takes some time to update the heating controller. So during this period, the mobile user interface and the controller display will show you two different numbers, 21 and 19, because they are out of sync until the controller do the polling and pull the information, download the information, which is the instruction, which is 21 to its controller unit. It would be quicker to push the instruction directly from the service to the gateway and to the device. But most of the routers nowadays have a single public IP, and then the local IP addresses are hidden from the internet. So it is difficult for a service to push or pull from directly from individual home networks. So that is why the importance of having IP for each device. If we had IP for each one and each independently connected to the internet, then there is a possibility that you can directly communicate. Security firewalls may also issue, because security firewalls usually configured to hide the local network from the internet. So internet, the malicious activities or malicious actors from the internet cannot directly sabotage the local network, because they can't address it. They don't know what is inside it. So because there's no push mechanism here, it will take until the device do the polling and see whether there's a new instruction for them, waiting for them in the cloud. The system remain out of sync. So this is going to be a typical scenario for most of the IoT devices, and this is applicable for all IoT devices, not only for this use case. The amount of polling that you can do has a trade-off, because if you do too much polling, that means you are consuming a lot of energy, and also the cloud services will get large amount of requests, because it is not about you, because if you're looking at large number of devices across different houses, then it becomes millions of devices, becomes millions of requests. And it is also interesting to see that in the previous figure, we realized that the controller is polling every 2 minutes, and the mobile is polling every 30 seconds. So technically, if we consider the same use case and then say the user went to the heating controller and then manually changed the heating controller, which will immediately increase the heating as well as update the user interface within the heating controller, and then it will push the update to the cloud service. And because the phone is polling so faster than the controller units, because 30 seconds versus 2 minutes, the entire system will get sync quickly than we thought previously, because previously it was 2 minutes. But still, there will be a 30-second gap between the out of sync period. When you are designing an IoT application, you need to think about the frequency of polling, because that will directly affect the energy consumption of the individual devices and how long the entire system can be operate without recharging part of the IoT system. In the heating scenario, the few minutes doesn't actually matter, because heating operates in time scale of longer minutes or even hours. It will take time to get the temperature increased. Nobody really cares. But if you consider a slightly different scenario, perhaps your IoT system has a segment where when an email received, the light bulbs light up, a smart light bulb, flash or change color or something. And then if you are polling the Gmail service or your email provider every 15 minutes, it will take a long time for you to at least 15 minutes. If you are very unlucky, if it will take 15 minutes to get a notification, which is not very responsive. The users might feel that they have significant delay in to get to know when the email comes in. So depending on the use case, you need to change the polling frequency, and also think about polling frequency from both ends if there are multiple ends, because in the previous use case we realized that the two components, both the mobile phone and the heating controller, has their own polling frequencies. And then what component has the more responsibility and more energy. So based on that, you need to make the decision how you're going to calculate the amount of minutes or seconds or hours or whatever the frequency of polling. But polling is going to be a significant part of IoT devices as long as we don't have the direct communication between IoT devices because they are behind the routers, behind the firewalls. So most easiest option is to always polling and pushing the data, pulling the data. So you check the server and then pull the data if there are any update, and then push your data to the cloud if you have any update. So the other parties might poll and push when they need it. Here I have summarized a few design thoughts. If you want the devices to respond quite quickly to commands, you need to either maintain an open connection, which is expensive, or you need to increase the polling frequency. And then polling when there's nothing new to share could place a lot of servers, load on the server, and also exhaust the battery. Because you need to think about that if you are designing one application for your company, that is fine. But if you are developing a product or service that is used by millions of people, then when the number of devices increase, the polling request increase. So you are talking about millions if you have millions of planning to sell millions of devices. But if you are an individual company and then you are doing some kind of deployment which have limited number of devices, increasing the polling might not be an issue as long as you have access to the energy. But again, if they are looking at deploying large number of devices like smart meters or something like that, then you need to think about the load on created by all these individual devices. Another design idea is that you can dynamically change the polling frequency. For example, if you are polling every 2 minutes and then as a heat detector, and then if you detect a possible fire or a heat source, you can increase the polling frequency from 2 minutes to every second for the next 20 minutes. And if it is like a false alarm, then you can reduce it back. And also you can think about to reaching the internet using different mechanisms. For example, if the device could not contact the usual gateway, it might hop through alternative nodes using a mesh network and try to get through any capable device who can pass the message to the internet. With the static IP, for example, if you assume that we have IPv6 and the appropriate applications in place, it could theoretically also try to use neighbors network if there are any emergency. Because if the particular devices can be identified uniquely, then there are a lot of flexibilities opens up, because now you can then the other networks can trust you. You can share your information because it is your own information. You have a virtual identity, so you can easy to ask someone else to trust your identity and share the detail and be able for them to verify your identity. But at the moment you are hiding behind a gateway, with changing local IP addresses. So for the outside world, it is not trustworthy. When you're designing an IoT application, especially if it is so critical as like elderly person's emergency button, so you need to think about at least 3 stages. First, you need to give feedback on whether the message has been sent from the eldest person end, and then you need to give the feedback that whether the other end, whoever the carer or emergency services, has received the message, that end, maybe that device. And then third is whether the other person on the other end has seen the message. So these are the 3 key steps that you need to ensure if it is a critical system. And also you need to think about any backup communication and connectivity, like if it is Wi-Fi fails, maybe a cellular connection or any other mesh network kind of arrangement to support secondary and tertiary backup requirements. A key consideration for user experience is to understand how quickly the data is passed around in a particular IoT system, and then what is the good fit for a particular context. For example, if it is a home energy monitoring system where they measure and monitor the electric usage of the last 24 hours, you could configure to send the data every few minutes or longer, and then keep deleting the data, and then the internet service will have the last 24 hours of data. So when somebody is requesting data, the data will be directly queried from the internet service, not directly coming from the energy meter. So the energy meter does not hold the data because it uploads all the data to the cloud every few minutes. This might be quicker, reduce the cellular data costs for your energy company. Because in this case, they are responding to the query by sending the data they have already. Otherwise, it takes time to query the actual device and get a feedback. So the data in the cloud or the internet service might be slightly older depending on how frequently the data get uploaded. But for an energy monitoring scenario, that is okay. However, if you are looking at a door lock system where you want to know whether your the door is locked and when it is open or closed, you don't want to have all data. You actually need the real-time data, including the number of hours of the historical log saying when it is open, when it is closed. So if you are sending all data which is 2 minutes or 5 minutes older, then you end up wondering what had happened the last 2 or 5 minutes, which will be updated every 2 to 5 minutes, because the door lock is sending data to the internet service 2 or 5 minutes. Then there is a gap always between the actual data points and the what is the data points in the cloud. So that kind of gap might not be acceptable for security systems or use cases like front door locks. So these are the different use case scenarios or design principles that you need to think about when you are designing IoT applications and selecting different choices we discussed throughout this lesson. Now we have reached the end of lesson number 7, human factors and interactions. I hope this lesson helped you to look at the IoT systems from human factors or design perspective and think about how the technologies that we'll discuss throughout this course need to be put in place in such a way that they are meaningful, practical, and useful in the context they are deployed, and they help the stakeholders to solve their own problems. We also highlighted the importance of the user-centric or the context-aware design, because sometimes the technology are really tempting to use particular technologies. However, they are even though they may be the most optimum, they may be not the best for the stakeholders or the end users to be used in a particular context. So I hope the design ideas that you learned throughout this lesson will help you to revise and rearrange some of the designs that you are developing from technology point of view previously now, but embedding some human and more user-centric ideas into the IoT systems design.